In this video, we're going to look at ordering some objects where they're not all distinct. If you think back to the last 5 videos with the techniques that we've done so far in this section, they're all about ordering distinct objects. This one, what happens if they're not all distinct? So, and how many distinguishable ways can we place the letters in the word abracadabra in order? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters there. So if we put those letters in order, there are 11 factorial ways of putting them in order. But some of those you can't tell apart because you got a bunch of A's. There's at least more than one B and so forth. And so some of those, switching the A's around doesn't change anything, or switching the B's around doesn't change the word, or at least the order of the letters. So if you count these up, we'll notice that there are 5 A's, 2 B's, 1 C, 1 D, and 2 R's for a total of 11 letters. So the way of ordering them all is 11 factorial of placing them in the order, but some of these are counted multiple times because you can't tell them apart. So if we need to divide this by the number of different ways of permuting around or putting in order the different A's, because we can't tell the A's apart, so that's 5 factorial ways, so we have to divide by that. Similarly, we have to divide by 2 factorial ways, the 2 different ways we can put the 2 B's. Switching the B's, 2 B's doesn't change it. Similarly, switching the 2 R's. So we can think of that as 11 factorial over 5 factorial times 2 factorial times 1 factorial times 1 factorial times 2 factorial. And if you work that out, that's 83,160. And so this leads to a general technique. So if we're given a collection of n objects of k different types, with objects of the same type being indistinguishable, meaning you can't tell them apart, where the number of each of the types are n1, n2, and so forth up to nk, and you add up these numbers of each type and you get the total number of objects, n, then the number of ways of distinguishable number of ways of ordering the objects is given by this formula. N factorial over the product from j equals 1 to k of n sub j factorial. So that's n factorial over n1 factorial, n2 factorial, n3 factorial, all the way up to n sub k factorial. Just like the one we just did with abracadabra. So let's try this again. Here's an exercise to see if you can apply this rule. How many distinct arrangements of the letters in economic are there? Okay, we're going to use all the letters, but we're going to look different orders. So the order matters here, but we want to be able to see how many ways we can put them in order and make sure we can tell all those different ways apart. So use the little formula or process that we just came up with and work it out. Press pause now. Well, counting up the letters, there are 2 C's, 1 E, 1 I, 1 M, 1 N, and 2 O's for a total of 8 letters. So the number of ways you can put them up is 8 factorial over 2 factorial, 1 factorial, 1 factorial, 1 factorial, 2 factorial. 1 factorial is, of course, 1. 2 factorials is just 2. So the denominator is 2 times 2 is 4. So you're just dividing out by 4. So it's 8 factorial divided by 4, which is 10,080. Here's another example. Let's try this one. How many different 9-digit numbers can be formed using the digits in the number 277, 728, 788? Notice that's 8 digits. We're going to use 9 digits. We're going to use all 9 of them, but some of them are repeats in the digits. So, how many ways could this happen? Figure this out. Press pause. Come back when you're ready. Well, there are 2 2's, 4 7's, and 3 8's for a total of 9 digits. So 9 digits total is 9 factorial for the numerator. The denominator is 2 factorial times 4 factorial times 3 factorial. Don't forget parentheses around the denominator. Work this out by hand or with a calculator. You get 1,260.